Well, welcome back to our course, Computer Organization and Architecture. For this lecture, we're going to be getting into cache memory. So let's go ahead and take a little bit of a chance to get an overview of what we're going to talk about in this chapter. In the very end, we'll come to this same slide and review these concepts. So we'll get into cache memory principles. So get familiar with the things that are done in terms of caching. We'll look at an example with the Intel x86 cache organization. And then, in contrast, we'll also get a chance to look at the IBM Z13 cache organization, so two different processors. We'll talk about cache performance modules, talk about the timing module and the design option for improving the performance, and then we'll look at the elements of cache design, looking at the cache address, the cache size, the logical cache organization, replacement algorithms, write policy, line size, number of caches, and inclusion policy. So a lot of information, maybe more than what you ever thought would be a part of what's going on for caching. So cache memory is designed to combine the memory access time of expensive high-speed memory combined with a large memory size of the expensive low-speed memory, the less expensive low-speed memory. The concept is illustrated in this figure that we're showing, figure 5.1a. There's a relatively large and slow main memory together with a small fast cache memory. So here we're introducing for the first time cache, and so we have a single one that we're talking about here. The cache contains a copy of portions of the main memory. When the processor attempts to read a word of memory, a check is made to determine if the word is in the cache. If so, the word is delivered to the processor. If not, a block of main memory consisting of some fixed number of words is read into the cache, and then the word is delivered to the processor. Because of the phenomenon of locality of reference, when a block of data is fetched into the cache to satisfy a single memory reference, it is likely that there will be a future reference to the same memory location or other words in the block. And then we have in figure 1.5.1.b, we have multiple caches here. So the L2 cache is slower than and typically larger than the L1 cache, and the L3 cache is slower and typically larger than the L2 cache. So we're seeing an organization of three different caches, and we'll get a chance to get some insight into, well, why would you actually do that? So let's go ahead and take some time to talk about some of the cache memory principles, some of these terms. We'll talk about block, frame, line, tag, and line size. And so block is a minimum unit of transfer between cache and main memory. In most of the literature, the term block refers to both to the unit of the data transferred and to the physical location in the memory, main memory, or cache. Next, frame, to distinguish between the data transferred and the chunk of physical memory. The term frame or lock frame is sometimes used with reference to caches. Some texts and some literature use the term with reference to the cache, and some will reference to the main memory. Its use is not necessary for the purpose of this text, but we want to basically give you a chance to understand what that is. Next, we have line. A line is a portion of cache memory capable of holding one block, so called because it usually is drawn. It's usually drawn as a horizontal object. That is, all bytes of the line are typically drawn in one row. A line also includes control information. Next, we have tag. A tag is a portion of the cache line that is used for addressing purposes. As we'll explain shortly, a cache line may also include other control bits, as will be shown. Memory consists of up to 2 to the n addressable words, with each word having a unique n-bit address. For mapping purposes, the memory is considered to consist of a number of fixed length blocks of k words each. That is, there are m to the 2n divided by k blocks in the main memory. The cache consists of m lines. Each line contains K words plus a tag. Each line also includes a control bits shown as a bit to indicate where the line has been modified since being loaded into the cache. The length of the line, not including the tag and the bits, is what's called the line size. That is, the term line size refers to the number of data bits or block size contained in the line. They may be as small as 32 bits, with each quote word being a single byte. In this case, the line size is 4 bytes. The number of lines is considerably less than the number of main memory blocks. That is, small m is much less than capital N. At any time, some subset of the blocks of memory resides in a line in the cache. In a word in a block of memory is read, that block is transferred to one of the lines of the cache. Because there are more blocks than lines, as an individual line cannot be uniquely and permanently dedicated to a particular block. Thus, each line includes a tag that identifies which particular block is currently being stored. The tag is usually a portion of the main memory address, as described later in this section. Okay, so we had this word chart. Now we get a chance to see some of these in terms of a figure. And so if you want, you can review this, pause the video, and go back and forth if you want to see the word chart. And here we're seeing the layout that we just spoke about. So for our cache, we have the tag, we have the blocks, and then we have the main memory. And so this is the things that were described in the last chart. Here we have another figure. This illustrates the read process. The process generates the read address, RA, of a word to be read. If the word is contained in the cache, that is, it has a cache hit that is delivered to the processor. And if it does find it, it doesn't have to go through all this extra processing to locate it and retrieve it from main memory. Okay, let's talk about the typical cache organization. If a cache miss occurs, two things must be accomplished. The block containing the word must be loaded into the cache, and the word must be delivered to the processor. When a block is brought into the cache in the event of a miss, the block is generally not transferred in a single event. Typically, the transfer size between cache and main memory is less than the line size, with 128 bytes being a typical line size, and a cache main memory transfer size of 64 bits, that's 2 bytes. To improve performance, the critical word first technique is commonly used. When there is a cache miss, the hardware requests the missed word first from memory and sends it to the processor as soon as it arrives. This enables the processor to continue executing while filling in the rest of the words in the block. So in figure 5.3, we showed that the last two operations occurred in parallel and reflects the organization shown in the figure we're showing here in figure 5.4, which is typical of contemporary cache organization. In this organization, the cache connects to the processor via data control and address lines. The data and address lines also attach to data and address buffers, which attach to a system bus for which main memory is reached. When a cache hit occurs, the data and address buffers are disabled, and communication is only between the processor and cache with no system bus traffic. When a cache miss occurs, the desired address is loaded into the system bus, and the data are returned through the data buffer to both the cache and the processor. Okay, so let's look at the elements of cache design. And so in the text, the section regarding this section provides an overview of the cache design parameters and reports some typical results. We occasionally refer to the use of cache in high performance computing. or HPC. High performance computing deals with supercomputers and their software, especially for scientific applications that involve large amounts of data, vector and matrix computation with the use of parallel algorithms. Cache design for HPC is quite different from other hardware platforms and applications. Indeed, many researchers have found that HPC applications perform poorly on computer architectures that employ caches. Other researchers have since shown that a cache hierarchy can be useful in improving performance if the application software is tuned to exploit the cache. So to have it be useful, you want to have things that are tuned for the cache utilization. Although there are a large number of cache implementations, there are a few basic design elements that serve to classify and differentiate cache architectures. Here in the table we're showing these elements. So we have cache addressing, we have cache size, we have mapping functions, we have a replacement algorithm, write policy, line size, and the number of caches. So this is stuff that we had mentioned at a very high level when we had our table of contents summary chart in the beginning, and we'll be getting into the details as we go. So let's talk about caching addresses and thinking about virtual memory. Almost all non-embedded processors and many embedded processors support virtual memory, concept discussed in more detail in Chapter 9. In essence, virtual memory is a facility that allows programs to address memory from a logical point of view without regards to the amount of main memory physically available. When virtual memory is used, the address fields of machine instructions contain virtual addresses for reads to and writes from main memory. A hardware memory management unit, an MMU, translate each virtual address into a physical address in main memory. When virtual addresses are used, a system designer may choose to place a cache between the processor and the MMU or between the MMU and the main memory. Figure 5.5, we had a logical cache known as a virtual cache, stores data using virtual addresses, and the processor accesses the cache directly without going through an MMU. A physical cache stores data using the memory physical address. And so those are a couple of possibilities here. One obvious advantage of the logical cache is that cache access speed is faster than for a physical cache because a cache can respond before an MMU performs an address translation. The disadvantage has to do with the fact that most virtual memory systems supply each application with the same virtual memory address space. That is, each application sees a virtual memory that starts at address 0. Thus, the same virtual address in two different applications refer to two different physical addresses. The cache memory must therefore be completely flushed with each application. Content switch or extra bits must be addressed to each line of the cache to identify which virtual address space the address refers to. So a couple things to be thinking about, and here we're referring to the figure. We first of all have a logical cache, and so we can see the layout here where the cache would be put in versus a physical cache, and so it's going to be on one side or the other of the MMU. So next, let's go ahead and talk about cache size. The second item in table 5.1, cache size, has already been discussed. We would like the size of the cache to be small enough so that the overall average cost per bit is close to that of the main memory alone, and large enough so that the overall average access time is close to that of the cache alone. So here we're trying to get the best of both worlds. There are several other motivations for minimizing cache size. The larger the cache, the larger number of gates involved in addressing the cache. The result is that large caches tend to be slightly slower than smaller caches. Even when built upon the same integrated circuit technology and put in the same place on a chip and a circuit board, the available chip size, the available chip and board area also limits cache because performance of the cache is very sensitive to the nature of the workload. It is impossible to arrive at a single, quote, optimal cache size for everything. And so those are things that have to be thought about. How are you going to actually be using the processor? Well, here we have a table that lists the cache sizes of some current and past processors. And so this goes back a way per se for the year of introduction. You can just think about this in general, just a hierarchy of starting from older going to newer. And you can see how initially they had a single cache, gradually getting up to having 2 caches and moving even higher to 3 caches. And we can see a little bit of information about the sizes of those. We can see the different manufacturers, the IBM, Intel being 2 of the larger ones. And there's a couple other things here. And I'm not going to get into the details of each of these because each one of them has an interesting story. And so we're going to be taking an example later, both for an IBM and an Intel, so you can be thinking about that as we move forward. Well, let's talk about cache access methods. Because there are fewer cache lines than main memory blocks, an algorithm is needed for mapping main memory blocks into cache lines. Further, a means is needed for determining which main memory block currently occupies a cache line. The choice of the mapping function dictates how the cache is logically organized. 3 techniques can be used: direct, associative, and set associative. And so these are the 3 things that we see listed here. We examine each of these in turn. In each case, we look at the general structure and then a specific example. So the table we're looking at, table 5.3, provides a summary of key characteristics of the 3 approaches. So we have the organization, the mapping of the main memory blocks to cache, and the access using the memory address. So let's talk about the direct and associative approach to mapping from main memory. The simplest technique is known as direct mapping. It maps each block of main memory into one possible cache line, and the mapping is expressed that I is equal to J modulo M, and hopefully most, or if not all of you, remember the modulo operator, say from data structures or other things where you can be thinking about it. You can think of module like thinking of like the time. The minutes in an hour is modulo 60, and so that's what we're trying to think of. And so where I is the cache line numbers, J is the main memory block number, and M is the number of lines in the cache. So in this figure that we're showing, 5.6a, it shows the mapping for the first M block of main memory. Each block of main memory maps into a unique line of the cache. The next M blocks of the main memory into the cache in the same fashion, that is, block BM of the main memory block maps into lines L0 of the cache, block BM plus 1 maps into lines L1, and so forth. And in the bottom here, we're showing another example called the associative mapping that we're not going to get into detail for now. So the mapping function is easily implemented using the main memory address. So figure 5.7 we're showing here illustrates the general mechanism. It indicates the logical structure of the cache hardware access mechanisms. When the cache hardware is presented with an address from the processor, the line number portion of the address is used to index into the cache. A compare function compares the tag of the line with the tag field of the address. If there is a match, that is a hit, an enable signal is sent to the select function, which uses the offset field of the address and the line number field of the address to read the desired word or byte from the cache. If there is no match, that is a miss, then a select function is not enabled and data is accessed from the main memory. or the next level of cache. So this figure illustrates the case in which the line number refers to the third line in the cache, and there is a match as indicated by the heavier arrowed line. The direct mapping technique is simple and inexpensive to implement. Its main disadvantage is that there is a fixed cache located for any given block. Thus, if the program happens to reference word repeatedly from two different blocks that map into the same line, then the blocks will be continually swapping in the cache and the hit ratio will be low, a phenomena that is called thrashing. So here we have a direct mapping example. I'm not going to go through this in detail, but just to give some of the basics. An example, m equals 16k equals 2 to the 15, and I is equal to j modulo 2 to the 14. And so you can go ahead and take advantage of reading about this more in the textbook. Note that no two blocks that map into the same line number have the same tag number. So that's something to be thinking about. And you can be referring to figure 5.3. A read operation works as follows. The cache system is presented with a 24-bit address, and so that we see it's partly tag and partly the line plus word. So the 14-bit number is used as an index into the cache to access a particular line. The 8-bit tag number matches the tag number currently stored in that line. Then the 2-bit word number is used to select one of the 4 bytes in that line. Otherwise, the 22-bit tag plus line field is used to fetch a block from the main memory. The actual address that is used for the fetch is the 22-bit tag plus line. Is the 22 tag plus line concatenated with 2 0 bits so that 4 bytes are fetched starting at the block boundary. So you have to think about that a little bit to get that down a little bit more. Okay, let's talk about content addressable memory. So before we can be talking about associative cache organization, we need to introduce the concept of content addressable memory, or CAM, also known as associative storage. CAM is constructed of static RAM, SRAM cells, and that's something that if you're not familiar about, we'll be getting a chance to touch about that a little bit more. But it is considerably more expensive and holds much less data than regular SRAM chips. Put another way, CAM with the same data capacity as a regular SRAM is about 60% larger. CAM is designed such that when a bit string is supplied, the CAM searches its entire memory in parallel for a match. If the content is found, the CAM returns the address where the match is found, and in some architectures also returns the associated data words. The processor only takes 1 clock cycle. So we can see that it can be fairly efficient in terms of how long it takes to do this operation. So we have 2 parts of this figure. In the top, figure 5.9a is a simplified illustration of the search function of a small CAM with 4 horizontal words. Each word contains 5 bits or cells. CAM cells contain both storage and comparison circuitry. There is a match line corresponding to each word feeding into the match line sense amplifiers, and there is a differential search line pair corresponding to each bit in the search word. The encoder maps these lines of the matching location to its encoded address. Moving on to the bottom of the figure in figure 5.9b, it shows a logical block diagram of a CAM or cell array consisting of m words of n bits each. Search, read, and write enable pins are used to enable one of these 3 operating modes of the CAM. For a search operation, the data to be searched is loaded in an n-bit search register that resets the logic states of the search lines. The logic within and between cells of a row is such that a match line is asserted if and only if the cell in a row match the search line values. A simple read operation as opposed to a search is performed to read the data stored in the storage nodes of the CAM cells using read enable control signal. The data were to be stored in CAM cell arrays are provided during a write operation through data input port. Okay, now we have a fully associative cache organization that we're showing in this figure. Associative mapping overcomes the disadvantage of direct mapping by permitting each main memory block to be loaded into any line of the cache. And so that was in figure 5.6b. In this case, the cache control logic interprets a memory address simply as a tag and a word field. The tag field uniquely identifies a block of main memory. To determine whether a block is in the cache control logic must simultaneously examine every line tag for a match. So the figure we're showing here illustrates the logic, figure 510. Note that no field in the address corresponds to the line number, so that the number of lines in the cache is not determined by the address format. Instead, if there is a hit, the line numbers of the hit is sent to the select function for the cache hardware as shown in figure 5.9. With associative memory mapping, there is flexibility as to which block is replaced when a new block is read into the cache. Replacement algorithms discussed later in the section are designed to maximize the hit ratio. The principal disadvantage of associative mapping is the complexity of the circuitry required to examine the tags of the cache lines in parallel. So here in figure 511, it shows an example using associative mapping. The main memory address consists of 22-bit tag and a 2-bit byte number. So we have that. The 22-bit tag must be stored with 32-bit block of data for each line in the cache. Note that it is the leftmost most significant 22 bits of the address that form the tag. Thus, the 24 hexadecimal address 16339C has a 22-bit tag 058C E7. And so you can be thinking of the binary representation of that, and we have a little bit of indication of that in this figure. With associative mapping, there is a flexibility as to which block to replace when a new block is read into the cache. Replacement algorithms discussed later in the section are designed to maximize the hit ratio. The principal disadvantage of associative mapping is a complex circuitry required to examine the tag of cache, to examine the tags of all the cache lines in parallel. So let's continue with set associative mapping. So set associative mapping is a compromise that exhibits the strengths of both the direct and associative approaches while reducing their disadvantage. In this case, a cache consists of a number sets, each of which consists of a number of lines. The relationship are M equals V times K, and I equals J modulo V, and we talked about the module operator before, where I is the cache set number, J is the main memory block number, M is the number of lines in the cache, and V is the number of sets, K is the number of lines in each set. This is referred to K-way set associative mapping, with set associative mapping block B sub J can be mapped into any of the lines of set I. And so this is what that looks like. So here in this figure 512A, it illustrates the mapping for the first V block of main memory as the associative mapping. Each word maps into multiple cache lines. For set associative mapping, each word maps into all the cache lines in a specific set, so that the main memory block B sub 0 maps into set 0 and so on. Thus, the set associative cache can be physically implemented as n-associative caches. It is also possible to implement the set associative cache as k-direct mapping caches, as shown in figure 512b. Each direct mapped cache is referred to as a way consisting of V lines. The first V lines of the main memory are direct mapped into V lines of each way. The next group of V lines of main memory are similarly mapped, and so on. The direct mapped implementation is typically used for small degrees of associatively small values of k, while the associative mapped implementation is typically used for higher degrees of associativity. Let's continue on. For set associative mapping, the cache control logic interprets a memory address as three fields: the tag, set, and word. The D set bits specify one of the 2 to the D sets. The S bits of the tag and set fields specify one of the 2 to the S blocks of main memory. So in this figure 513, it illustrates the cache control logic with fully associative mapping. That the tag in a memory address is quite large and must be compared to the tag of every line in the cache. With k-way set associative mapping, the tag in a memory address is much smaller and is only compared to the k tags within a single set. As was shown in figure 512, if there is match of tags on any of the lines in the set, the corresponding select function is enabled and retrieves the desired work. If all comparisons report a miss, then the desired word is retrieved from the main memory. So in this figure, we're showing an example using a set associative mapping with 2 lines in each set referring to referred to as two-way set associative. The 13-bit set number identifies a unique set of 2 lines within the cache. It also gives the number of the block in main memory, modulo 2 to the 13. This determines the mapping of block lines. The block lines of the main memory mapped into cache set 0. Any of those blocks can be loaded into either of the 2 lines in the set. Note that no 2 blocks that map into the same cache have the same tag number. For a read operation, the 13-bit set number is used to determine which set of 2 lines is to be examined. Both lines in the set are examined for a match with the tag number of the address to be accessed. Okay, there are some extreme cases. In the extreme case of V equals M, K equals 1, the set associative technique reduces to the direct mapping. And for V equals 1, K equals M, it reduces to the associative mapping. The use of 2 lines per set, V equals M over 2 and K equals 2, is the most common set associative organization. It significantly improves the hit ratio over direct mapping. 4-way set associative, that's with V equals M over 4, K equals 4, makes a modest additional improvement for a relatively small additional cost. Further increase in the number of lines per set has little effect, and so we can see a sweet spot is starting to be worked out, which is one of the things that can be significant as continued computational architecture research goes on. So in this figure, we're showing the results of one simulation study of a set associative cache performance as a function of cache size. The difference in performance between direct and 2-way set associative is significant, up to at least a cache size of 64. And so we're seeing this here in the figure. Note that the difference between two-way and four-way at 4 kilobit is much less than the difference, and it goes from 4 kilobit to 8 kilobit in cache size. The complexity of the cache increases in proportion to the associativity, and in the case would not be justifiable against increasing cache size to 8 or 16 kilobytes. A final point to note is that beyond about 32 kilobytes, increase in cache size brings no significant increase in performance. The results of figure 515 are based on simulations simulating the execution of the GCC compiler. Different applications may yield different results. So those are some things that you can be thinking about. Well, what about replacement algorithms? Once the cache has been filled, when a new block is brought into the cache, one of the existing blocks must be replaced. For direct mapping, there is only one possible line for a particular block and no choice for it is possible. For the associative and set associative techniques, a replacement algorithm is needed. To achieve high speed, such an algorithm must be implemented in hardware. So those are some considerations. A number of algorithms have been tried. There are things that we've already mentioned. We mentioned 4 of the most common. Probably the most effective is least recently used, LRU. And so what it does, it replaces the block in the set that has been in the cache the longest with no reference to it. For two-way set associative, this is easily implemented. Each line includes a use bit. When a line is referenced, its use bit is set to 1, and the use bit of the other lines is set to 0. When a block is to be read into the set, the line whose use bit is 0 is used. Because we are assuming that more recently used memory locations are more likely to be referenced, LRU should give the best hit ratio. LRU is also relatively easy to implement for a fully associative cache. The cache mechanism maintains a separate list of indexing to all the lines in the cache. When a line is referenced, it moves to the front of the list. For replacement, the line at the back of the list is used. Because of its simplicity of implementation, LRU is the most popular replacement algorithm. Another possibility is the first in, first out, FIFO. For this case, the algorithm is to replace that block in the set that has been in the cache the longest. The FIFO is easily implemented as a round robin or circular buffer technique. Maybe you recall a circular buffer. Just as a hint, the module operator is one of the things that can be helpful for thinking about how you go about doing that. Still, another possibility is least frequently used. So the algorithm is to replace that block in the set that has experienced the fewest references. The LFU could be implemented by associating a counter with each line. A technique not based on usage is to pick a line at random from among the candidate lines. Simulation studies have shown that random replacement provides only slightly inferior performance to its algorithm based on usage. So those are some perspectives, and yet some tempering things that go outside of having an algorithm just by choosing it at random. Well, let's next talk about write policy. When a block that is resident in the cache is to be replaced, there are 2 cases to consider. If the old block in the cache has not been altered, then it may be overwritten with a new block without first writing out the old block. If at least one write operation has been performed on a word in that line of the cache, then the main memory must be updated by writing the lines of the cache out to the block of main memory before bringing in the new block. A variety of write policies with performance and economic trade-offs is possible. There are 2 problems to consider first. Let's think for the first one is more than one device may have access to main memory. For example, an I/O module may be able to read/write directly to memory. If a word has been altered only in the cache, then the corresponding memory word is invalid. Further, if I/O devices have altered main memory, then the cache word is invalid. A more complex problem occurs when multiple processors are attached to the same bus and each processor has its own local cache. Then, if a word is altered in one cache, it would conceivably invalidate a word in the other cache. So we can be seeing these concerns of how we need to synchronize writing so we have consistent data. Well, what about write through and write back? The simplest technique is called write through. Using this technique, all the write operations are made to main memory as well as to the cache, ensuring the main memory is always valid. Any other processor cache module can monitor traffic to main memory to maintain consistency with its own cache. The main disadvantage of this technique is it generates substantial memory traffic and may create a bottleneck. An alternative technique is known as a write back, and it minimizes memory writes. With write back, updates are made only in the cache. When an update occurs, a dirty bit or use bit associated with the line is set. When a block is replaced, it writes back to main memory if and only if the dirty bit is set. The problem with write back is the portion of main memory are invalid, and hence accesses by I/O modules can be allowed only through the cache. This makes for complex circuitry and a potential bottleneck. Experience has shown that the percentage of memory references that are writes is on the order of 15%. However, for a high-performance computing application, the number may approach 33% and go as high as 50%. So those are some things that if you want, you can read more about in the textbook. What about write-miss alternatives? There is another dimension in the write policy when a miss occurs at cache level. These are two alternatives to the event of a write-miss. First, we have write allocate, that the block contains the word to be written is fetched from the main memory or the next level cache into the cache, and the processor proceeds with the write cycle. The other possibility is a no write allocate. The block contains a word to be written is modified in the main memory and not loaded into the cache. Either of these policies can be used with either write through or write back. Most commonly, no write allocate is used with write through. The reason is that even if locality holds and a write will be made to the same block in the near future, the write through policy will generate a write to main memory anyway, so bringing the block into the cache does not seem efficient. For example, the ARM Cortex processors can be configured to use write allocate or write allocate with write back, but only no write allocate with write through. With write back, write allocate is most commonly used, although some systems such as the ARM Cortex also allow no write allocate. The reasoning for using write allocate is that subsequent writes to the same block, if the block originally caused a miss, will hit in the cache next time, setting the dirty bit for the block. That will eliminate extra memory access and result in efficient execution. The write back no write allocate option eliminates the time spent in bringing a block into cache. Depending on the locality pattern for reads and write, there may be some advantages to this technique. Okay, let's talk here about memory coherency. So we've been thinking about a couple of different ways of how we can be doing writing. We've introduced different techniques for managing the caching. Now let's be thinking a little bit more about coherency when there's all kinds of possible sources of access for read writes to the memory in the various caches. In a bus organization in which more than one device, typically a processor, has a cache and a main memory is shared, a new problem is introduced. If data in one cache are altered, this invalidates not only the corresponding word in main memory, but also the same word in other caches, if any of the other caches happen to have that same word. Even if a write-through policy is used, the other caches may contain invalid data. A system that prevents this problem is said to maintain cache coherency. Possible approaches to cache coherency include the following. First, we have the bus watching with write-through. In this case, each cache controller monitors the address lines to detect write operations to memory by other bus masters. If another master writes to a location in shared memory that also resides in the cache memory, the cache controller invalidates the cache entry. This strategy depends on the use of a write-through policy for all cache controllers. Another possibility is hardware transparency. Additional hardware is used to ensure that all updates to main memory via cache are reflected in all caches. Thus, if one processor modifies a word in its cache, this update is written to main memory. In addition, any matching word in other caches are similarly updated. And then finally, we have the non-cacheable memory. Only a portion of main memory is shared by more than one processor, and this is designated as non-cacheable. In such a system, all accesses to shared memory are cache misses. Because the shared memory is never copied into the cache, the non-cacheable memory can be identified using chip select logic or high address bits. Okay, let's talk about line size. And so another design element is the line size. When a block of data is retrieved and placed in the cache, not only the desired word, but also some number of adjacent words are retrieved. As the block size increases from very small to very large size, the hit ratio will at first increase because the principle of locality, which states that the data in the vicinity of the reference word are likely to be referenced in the near future. As the block size increases, more useful data are brought into the cache. This hit ratio will begin to decrease, however, as the block becomes even bigger and the probability of using the newly fetched information becomes less, than the probability of reusing the information that has to be replaced. The two specific effects come into play. Larger blocks reduce the number of blocks that fit into a cache because each block fetch overwrites older cache contents. A small number of blocks results in data being overwritten shortly after they are fetched. As a block becomes larger, each additional word is farther from the fetched word and therefore less likely to be needed in the near future. The relationship between block size and hit ratio is complex depending on the locality characteristics of a particular program, and no definitive optimum value has been found. A size from 8 to 64 bytes seems reasonably close to optimum. For high-performance computing systems, 64 to 128 byte cache size are most frequently used. What about multi-level caches? We have been talking about it, and so now let's be thinking about that, how that actually improves performance and why. As logic density has increased, it has become impossible to have a cache on the same chip as the processor. The on-chip cache. Compared with a cache reachable via an external bus, the on-chip cache reduces the processor's external bus activity and therefore speeds up execution times and increases overall system performance. When the requested instructions or data is found in the on-chip cache, the bus access is eliminated. Because of the short data paths internal to the processor compared with bus lengths, on-chip cache accesses will complete appreciably faster than would even zero-weight states bus cycles. Furthermore, during this period, The bus is free to support other transfers. The inclusion of an on-chip cache leaves open the question of whether an off-chip or external cache is still desirable. Typically, the answer is yes, and most contemporary designs include both on-chip and external caches. The simplest such organization is known as the two-level cache, with the internal cache designated as level 1, L1, and the external cache is designated as level 2, L2. The reason for including an L2 cache is as follows. If there is no L2 cache and the processor makes an access request for memory locations not in L1, then the processor must access DRAM or ROM memory across the bus. Due to the typically slow bus speed and slow memory access time, the result is poor performance. On the other hand, if an L2 SRAM static RAM cache is used, then frequently the missing information can be quickly retrieved. If the SRAM is fast enough to match the bus speed, then the data can be accessed using a zero-wait state transaction, the fastest type of bus transfer. The two features of contemporary cache design for multi-level caches are noteworthy. First, for the off-chip L2 cache, many designs do not use a system bus as the path for transfer between the L2 cache and the processor, but use a separate data path so as to reduce the burden on the system bus. Second, with the continued shrinkage of processor components, a number of processors now incorporate the L2 cache on the processor chip, improving performance yet again. The potential savings due to the use of an L2 cache depends on the hit ratio in both the L1 and the L2 caches. Several studies have shown in general that a second level cache does improve performance. However, the use of the multi-level cache does complicate all of the design issues related to cache, including size, replacement algorithms, and write policy. So those are things to be considered. Here in this figure 516, it shows the results of one simulation study of two-level cache performance as a function of cache size. The figure assumes that both caches have the same size, the same line size, and show the total hit ratio. That is, the hit is counted if the desired data appears in either the L1 or the L2 cache. The figure shows the impact of L2 on the total hits with respect to the L1 size. L2 has little effect on the total number of cache hits until it is at least double the L1 cache size. Note that the steepest part of the slope for L1 cache of the 8 kilobytes is for L2 cache of 16 kilobytes. Again, for the L1 cache of 16 kilobytes, the steepest part of the curve is for an L2 cache size of 32 kilobytes. Prior to that point, the L2 cache has little, if any, impact on the total cache performance. The need for L2 cache to be larger than L1 cache to affect performance makes sense if the L2 cache has the same size, the same line size and capacity as the L1 cache. It contends with more or less mirror those of the L1 cache. With increasing availability of on-chip area available for cache, most contemporary microprocessors have moved the L2 cache onto the processor chip and added an L3 cache. Originally, the L3 cache was accessible over the external bus. More recently, most microprocessors have incorporated an on-chip L3 cache. In either case, there appears to be performance advantages to adding the third level of caching. Furthermore, large systems such as the IBM mainframe Z enterprise system now incorporated 3 on-chip cache levels and a 4th level of caching shared across the multiple chips. So we're seeing in research and in advanced processors, there is an increasing number of caches that are being used, and they're moving them onto the actual processor chip as time goes by. Okay, well, let's now talk about unified versus split caches. When the on-chip cache first made an appearance, many of the designs consisted of a single cache used to store references to both data and instruction. More recently, it has been common to split the cache into two, one dedicated to instructions and the one dedicated to data. These two caches both exist at the same level, typically as two L1 caches. When the processor attempts to fetch an instruction from main memory, it first consults the instruction L1 cache, and then the processor attempts to fetch data from the main memory. It first consults the data L1 cache. There are two potential advantages of a unifying cache. For a given cache size, a unifying cache has a higher hit rate than a split cache because it balances the load between instructions and data fetches automatically. That is, if an execution pattern involves many more instruction fetches than the data fetches, then the cache will tend to fill up with instructions, and if the execution pattern involves relatively more data fetches, the opposite will occur. Only one cache is needed to be designed and implemented. The trend is towards split caches at the L1 and unified caches for higher level patterns for superscalar machines, would emphasize parallel instruction execution and the prefetching of predicted future instructions. The key advantage of the split cache design is that it eliminates contention for the cache between the instruction fetch/decode unit and the execution unit. This is important in any design that relies on the pipelining of instructions. Typically, the processor will fetch instructions ahead of time and fill a buffer or pipeline with instructions to be executed. Suppose now that we have a unified instruction data cache. When the execution unit performs a memory access to load and store data, the request is submitted to the unified cache. If at the same time the instruction prefetcher uses a read request to the cache for an instruction, that request will be temporarily blocked so that the cache can service the execution unit first, enabling it to complete the current executing instruction. This cache contention can degrade performance by interfering with efficient use of the instruction pipeline. The split cache structure overcomes this difficulty. So we're seeing some plus and minuses of how we could go about doing that. Let's talk about inclusion policy. So recall from chapter 4 that we defined the inclusion principle for memory hierarchy as followed. All information items are originally stored in level M sub n, where n is the level most remote from the processor, that is the lowest level. During the processing subset of M sub n, all copies into M sub n minus 1. Similarly, subsets of M sub n minus 1 are copied into M sub n minus 2, and so on. This is expressed concisely as mi plus 1. Thus, if all words are found in mi, then copies of the same word also exist in the lower layers, m sub I sub 1, m sub I plus 2, all the way up to m sub n. In multi-level cache environments in which there may be multiple caches at one level that share the same cache at the next lower level, inclusion between these two levels may not always be desirable. 3 inclusion policies are found in contemporary cache systems. This is what we're showing here in the chart. First is the inclusion policy. It dictates that inclusive policy dictates that a piece of data in one cache is guaranteed to be found at all lower level of caches. The advantage of the inclusive policy is that it simplifies searching for data when there are multiple processors in the computing system. For example, if one processor waits to know whether another processor has the data it needs, it does not need to search all levels of cache of the other processors, but only the lowest level cache. This property is useful in enforcing cache coherence, which is discussed in chapter 20. Next, we have the inclusive policy. It dictates that a piece of data in one cache is guaranteed not to be found in all the lower levels of cache. The advantage of the exclusive policy is that it does not waste cache capacity since it does not store multiple copies of the same data in all the caches. The disadvantage is the need to search multiple cache levels when invalidating or updating a block. To minimize the search time, the higher level tag sets are typically duplicated at the lowest cache levels to centralize searching. Finally, we have the non-inclusive policy. So with this one, we have a piece of data in one cache may or may not be found in lower levels of cache. This can be contrasted with the other two policies with the following examples. Suppose that the L2 line size is a multiple of the L1 line size. For the inclusive policy, if a block is evicted from the L2 cache, the corresponding multiple blocks will be evicted from the L1 cache. In contrast with the non-inclusive policy, the L1 cache may retain portions of the block recently evicted from the L2 cache. For the same difference in block sizes, if a portion of the block is promoted from the L2 cache to the L1 cache, the exclusive policy requires the entire L2 block be evicted. In contrast, the non-inclusive policy does not require this eviction. As with the exclusive policy, a non-inclusive policy will generally maintain all higher level cache sets at the lowest cache level. Okay, that's a lot of information that we got there. Let's now think about the evolution of cache. Let's think about this from an Intel point of view. So the evolution of cache organization is seen clearly in the evolution of the Intel microprocessors. And here, this table 5.4, the 8386 does not include on-chip cache. So the 8846 includes a single on-chip cache of 8 kilobytes using a line size of 16 bytes and a 4-way set associative organization. All of the Pentium processors included the 2 on-chip L1 caches, one for data, one for instructions. For the Pentium 4, the L1 data cache is 16 kilobytes using a line size of 64 bytes and a 4-way set associative organization. The Pentium 4 instruction cache is described subsequently. The Pentium 2 also included an L2 cache that feeds both the L1 caches. The L2 cache is 8-way set associative with a size of 512 kilobytes and a line size of 128 bytes. An L3 cache was added for the Pentium 3 and became on-chip with high-end versions of Pentium 4. Here in this figure, 517 provides a simplified view of the Pentium 4 organization, highlighting the placement of the 3 caches. This cache architecture is similar to those of the more modern x86 systems. The processor core consists of 4 main components. The fetch/decode unit fetches programs instructions in order from the L2 cache, decodes these into a series of micro operations, and stores the results in the L1 instruction cache. The out-of-order execution logic, it schedules the execution of the micro operations subject to data dependencies and resources available. Thus, micro operations may be scheduled for execution in a different order than the way that they were fetched from the instruction streams. As time permits, the unit schedules speculative execution of micro operations that may be required in the future. The execution units, these units execute micro operations, fetching the required data from the L1 data cache and temporarily storing the results in registers. Then we have the memory subsystems. This unit includes the L2 and the L3 cache and the system bus, which is used to access main memory when the L1 and L2 cache have a cache miss and to access the system IO resources. unlike the organization used in all previous Pentium modules and in most other processors, the Pentium 4 instruction cache sits between the instruction decode logic and the execution core. The reason behind this design decision are as follows. As discussed more thoroughly in Chapter 18, the Pentium processor decodes or translates Pentium machine instruction into simple RISC-like instruction, reduced instruction set computing instructions called micro operations. The use of simple fixed-length micro operations enables the use of superscalar pipeline and scheduling techniques that enhance performance. However, the Pentium machine instructions are cumbersome to decode. They have a variable number of bytes and many different options. It turns out that performance is enhanced if this decoding is done independently of the scheduling and pipeline logic. We'll return to this topic in Chapter 18. The data cache policy employs a write-back policy. Data are written to the main memory only when they are removed from the cache and there has been an update. The Pentium 4 processor can be dynamically configured to support write-through caching. Here, we're looking at the Pentium 4 cache operating modes. The L1 cache is controlled by 2 bits in one of the control registers, labeled the CD, the cache disable, and NW, the not write-through bits in table 5.5 that we're showing. So there are also 2 Pentium 4 instructions that can be used to control the data cache. The INVD invalidates, flushes, that is, the internal cache memory, and signals the external cache, if any, to invalidate, and the WB INVD writes back any writes back and invalidates internal cache, and then writes back and invalidates external cache. Now we've been talking a lot about the Intel. Let's talk about the IBM. So the IBM Z13, and so it illustrates the logical interconnects of the Z13 cache system, showing the structure of a single processor drawer. A maximum system called a central processing complex, CPC, consists of 4 drawers. Each drawer consists of 2 processor nodes, with each node containing 3 processor units, PU, chips, and 1 storage controls, SC chip. The PU includes up to 8 cores. The L1, L2, and L3 caches are contained on each PU chip, and a separate SC chip holds the L4 cache for a processor node. Thus, a maximum configuration contains 192 cores. And just as a reminder, we're seeing 4 caches that are used in this type of a design. Some key characteristics of each layers are: 1, the L1 cache. Each core contains a 64 kilobyte L1 cache and 128 kilobyte D cache for a maximum total of 18 megabytes of L1 cache and 24 megabytes of L2 D cache. The L1 cache are designed as write-through caches. The L2 cache, each core contains a 2 megabyte L2 cache and a 2 megabyte L2 D cache for a maximum total of 384 megabytes of L2 cache and 384 megabyte of L2 D cache. The L2 cache are designed as write-through caches. The L3 cache, each PU contains 64 megabytes L3 cache for a maximum total of 1.5 gigabyte of L3 cache. The L3 cache is 16-way set associative and uses a line size of 256 bytes. The L3 cache uses the write-back policy. The L4 cache, each processor node contains a maximum of 480 megabytes of L4 cache for a maximum total of 3.75 gigabytes of L4 cache. The L4 cache is organized as a 30-way set associative cache. The L4 cache uses the write-back policy. So we're seeing some pretty complicated architecture here. The use of the L3 cache that is shared by 8 core on a chip facilitates low latency cross-processor cache line sharing and provides cache efficiency effects by the elimination of redundant lines, single copy / multiple users, which is not possible with private caches. Thus, there are efficiency gains by devoting a subsequent portion of each PU chip to a shared L3 cache as opposed to either increasing the size of the L2 cache or providing private L3 cache for each core. There are also efficiency benefits for providing an L4 cache chip on the same processor node or motherboard as the PU chip. The L4 cache enables smoother scaling from a single processor chip to a maximum system configuration by providing a significant buffer before main memory. The interconnection design contributes to the overall efficiency of the arrangement. Within each PU chip, 160 gigabytes per second bus bandwidth is used between the L1, L2, and the L2, L3 cache boundaries. The 80 gigabytes per second X bus provides tightly coupled interconnections within a node at the L3, L4 cache boundary. A high-speed S bus connects via L4 between the nodes of the drawers, and A bus connections are provided to other drawers. The cache write policy is tailored to the configuration. The L1 and L2 caches are write through, taking advantage of the high-speed on-chip connection to the next cache level. Further, the L3 cache is most efficiently used if it always maintains the most recent version of any L2 cache line. Going from L3 to L4 is a lower speed off-chip transmission, and here a write-back policy is preferred to minimize traffic. Similarly, write-back is preferred going from L4 to main memory. Okay, we're getting down to the final stretch for this chapter here. Let's go ahead and talk about cache timing models. We can derive some insight into the timing differences between the different cache access models by developing equations that show the different time delays. And so these are the things that are going to be shown in the next 2 charts here. And so just keep this in mind. We're just trying to give set it up before we get into that. And so CT is the time needed to compare the tag field of the address with the tag value at a cache time. T sub RL is the time needed to read a line from the cache to retrieve the data block in the cache. T sub XB is the time needed to transmit bytes or words to the processor. This includes extracting the desired bytes from the fetch lines and gating these bytes onto the bus to the processor. The T hit is the time expended at this cache level in the event of a hit. The T miss is the time expended at the cache level in the event of a miss. So first, consider direct mapping cache. So we're looking at the details of this chart now. The first operation is checking the tag field of the address against the tag value in the line desired by the line field. If there is not a match, that is, there's a miss, then the operation is complete. If there is a match hit, then the cache hardware reads a data block from the line in the cache and then fetches the bytes or words indicated by the offset field of the address. One of the advantages of the direct mapped cache is that it allows simple and fast speculation. Once the address has been computed, the one cache line that might have a copy of that location in memory is known. That cache entry can be read, and the processor can continue to work with that data before it finishes checking that the tag actually matches the required address. Thus, checking and fetching are performed in parallel. Next, consider a fully associative cache. In this case, the line numbers is not known until the tag comparison is completed. So the hit time is the time is the same as for direct map. because this is a content addressable memory, the missed time is simply the tag comparison time. That is, the tag comparison is made without the need to read a line of the data from the cache, but it is made in parallel to all the lines of the cache internal to the cache. With a set associative, it is not possible to transmit bytes and compare tags in parallel as can be done with the direct mapped with speculative access. However, the circuitry can be designed so that the data blocks from each line in a set can be loaded and then transmitted once a tag check is made. And thus we have these two charts that once you review what we talked about in the last chart and the description I was showing here, you can see the time for a hit, the time for a miss for these different types of cases here. So this is for the cache timing equations. And then in this chart, we have the cache performance improving techniques. And this is the last chart that we'll have before we do our summary here. So you can feel free to look over those in more detail. And so let's just review. We actually covered a lot of ground. We went over cache memory principles. We looked at two different cache organizations, the Intel approach and also the IBM approach. We talked about cache performance modules, cache timing. We talked about options for improving performance. And then we got into a lot of details of the cache design, the addressing, the cache sizes, having multiple caches, having a logical cache organization, replacement algorithms, write policy, line size, thinking of the number of caches, as well as the size, and finally the inclusion policy. So thank you very much.